We are excited to present our research, titled Beyond Average, Individualized Visual Scanpath Prediction. This work, authored by Xianyu Chen, Ming Jiang, and Zhao from the University of Minnesota, delves into a novel area of human attention modeling, predicting how an observer's unique characteristics influence their eye movements while performing visual tasks. Our visual experiences are inherently subjective and shaped by our individual backgrounds, interests, and goals. Most existing models treat everyone the same and predict a generic sequence of eye movements that focus on salient areas. These models can tell us where people tend to look in general, but they miss the fascinating details, how you look at the world compared to someone else. This gap in understanding individual differences is what our research aims to address. As shown in these examples, while one person might be drawn to the emotional expressions on faces, others might focus on the details of objects or the overall layout of the scene. Such variations can be attributed to various factors, such as gender, age, and even neurodevelopmental conditions of the observer. Therefore, developing tailored models that capture these individualities is crucial for more precise and adaptive attention modeling. In this work, we introduce individualized scanpath prediction, a new approach to modeling human eye movements that considers each observer's distinct attention preferences. Given the task description, the stimulus, and the subject, this approach can seamlessly integrate with existing architectures, such as LSTM and transformers, to produce a precise prediction of the corresponding individual's unique scan path. Particularly, our model consists of three novel components. First, our observer encoder acts as the foundation, extracting an observer embedding that captures each observer's unique attentional traits. Second, observer-centric feature integration is a component that facilitates the seamless fusion of various informative inputs, including visual features, task context, and the observer embedding. By consolidating this information, it creates a comprehensive representation tailored to each observer. Finally, an adaptive fixation prioritization module dynamically prioritizes relevant semantic feature maps based on the observer's unique attentional characteristics, ultimately leading to more precise predictions. These novel components are designed to be flexible as they can be applied on a general scanpath model based on the encoder-decoder architecture. At the core of our proposed method is an observer encoder, a key component designed to enable the novel task of individualized scanpath prediction. It takes as input an observer-specific identifier and efficiently computes an observer feature to represent the unique characteristics and preferences of each observer. It highlights the role of encoding the attention traits of different observers, resulting in more accurate and individualized scanpath predictions for each observer. With the encoded observer features characterizing each observer's distinct attention traits, we design observer-centric feature integration to address the critical need to fuse various inputs, including visual features, task relevance, and observer-specific characteristics, into a unified representation. The motivation behind this integration is to create a comprehensive understanding of individualized attention patterns. By the seamless integration of various input features, it yields more precise and tailored predictions of individual scan paths. While the observer-centric feature integration focuses on the fusion of input features, the adaptive fixation prioritization module addresses the variations of gaze behavior at the output end of the decoder. To achieve this, instead of directly predicting fixation positions, our approach, aimed at individualizing fixation predictions, takes a distinct path. The fixation prioritization's ability to prioritize where to look at the output end benefits the discriminative scanpath predictions for each observer. With these novel contributions, our method significantly improves the value-based metrics, which measure the similarity or dissimilarity between the prediction and ground truth scan paths of the same observer. The proposed ISP models consistently outperform the general methods and fine-tuning, indicating their ability to adapt to the unique attention traits of observers. Furthermore, we employ ranking-based metrics to evaluate how well the model predicts distinctly different scan paths for different observers. The individualized models achieve promising results across all metrics and datasets. It suggests that the ISP models can predict scan paths that align closely with an observer's unique attention traits. To evaluate the significance of the three technical components, we conduct an ablation study on the OSIE-ASD dataset by applying them incrementally to the two different baseline models. The fundamental module OE results in a significant improvement in the value-based evaluation and highlights its role of encoding attention traits of observers. Furthermore, based on OE, both FI and FP have notable impacts on the model performance. Both components achieve similar performance improvements in value-based metric, demonstrating their ability to improve the overall accuracy of scan path predictions. Further, regarding the ranking-based metrics, FI results in more significant improvements than FP, suggesting that the seamless integration of various input features is more substantial than FP's ability to prioritize where to look at the output end, indicating that FI and FP offer complementary enhancements. To understand how the predicted scan paths align with observer-specific gaze patterns, we present a qualitative comparison. It can be seen that the observer looks at different objects even given the same image and the task. Notably, while the fine-tuning approach falls short in capturing observer-specific gaze patterns, the ISP model's predictions better align with the scan paths of the human observers. This capability of ISP models opens up new avenues for understanding and interpreting individual differences in visual perception and decision-making processes. To evaluate how the predicted scan paths resemble human fixation statistics, we rank observers by their proportion of fixations in each category. While fine-tuning is less effective, showing low correlations across all categories, ISP models consistently achieve significant and high positive correlations, suggesting their ability to resemble each human observer's unique fixation patterns. Beyond individual characterization, ISP models also effectively capture and reproduce distinctive attention traits observed at the population level. The statistical agreement between the model predictions and the ground truth scan paths demonstrates our method's ability to generalize and represent population-level characteristics, reinforcing its potential utility in a variety of applications. We introduce a novel approach to predicting individualized human visual scan paths. It has three novel contributions. First, we propose an observer encoder to characterize and integrate an observer's unique attention traits. Second, we incorporate an observer-centric feature integration approach that holistically combines visual features, task guidance, and observer-specific characteristics. Finally, we use an adaptive fixation prioritization mechanism that refines scan path predictions by dynamically prioritizing semantic feature maps based on individual observers' attention traits. Our method is generally applicable to different datasets, model architectures, and visual tasks, offering a comprehensive tool for transforming general scan path models into individualized ones. Our source code is publicly available. For more details, please refer to our paper.